pi times the radius here, right? Use a fractional kind of argument. So the whole thing keys on the idea that the sun is right over, right on this radial line going down to Said on June 22nd, and he measures this angle at 20 degrees on the same day. And we have that distance there at 5,000 stadia. So we put together a fraction. It's a ratio thing. We know there's 360 degrees in a circle, all the way around a circle, right? So we know that the 7.2 degrees, the fraction of 7.2 degrees out of 360 has to be the exact fraction of that part of that distance over the full circumference of the Earth, the ratio. So this little angle here, 7.2 degrees, has to have the same relationship to the 360 that the 5,000 stadia has to the full circumference of the Earth. Okay, does that make sense? Simple fractional thing. I mean, if the distance were like, if this distance was stretched out to be half, somehow half, you know, if we were looking at opposite sides of the Earth or something, then you'd have 1/2. You'd have, this angle would actually be 180. If 180 over 360, then the distance would be half of the full circumference. Makes sense. So this ratio argument is what he actually uses. What he's trying to do is compute the radius of the Earth, which is the r there. So it's just a fraction, right? I mean, all the numbers in that equation are known except the capital R for the radius of the Earth. So what we do is we solve this equation. We multiply both sides by capital R, which gets rid of the capital R there, and it gives us one over here. And then we multiply both sides by 360 over 7.2. So we're just isolating the R factor. And when we do that, well, it's just the same thing again. Actually show that. Actually show that step. But anyway, we solve it algebraically. What we actually get is 39,789 stadia. Okay, that's not too meaningful if you don't know what a stadia unit is. You know, it's a weird unit from the Romans or something like that. But we know from historical, certain places we're given distances of stadia, and then we can measure them in modern units and get the conversion factor. That's pretty easy to do. So a stadium is about 0.16 kilometers. And so now we can do the math and convert the radius of the Earth from stadia to kilometers, and we get 6,366. That's actually incredibly close to the correct satellite operations. Modern satellite operations give a number that's amazingly close. I mean, we're talking about actually less than 1% error. Really. There's a good difference between those two numbers. 1% of the actual number would be about 60 kilometers, and the difference between is less than that. So it's less than 1% error. Really pretty amazing. And of course, we know, by the way, the Earth is perfectly spherical with a little bit of equatorial bulge, but the average radius is that value. Okay. And he has a crater named after him, crater Radisson. So measure the Earth's geometry, get a crater. It's been done already, but it doesn't make it. And this is back at times when, of course, we didn't even have the full layout of continents on the Earth, naturally. Or by West, and that's a Atari video. It's pretty funny that one. Moment. All right, so let's start talking about planetary motions a little bit. Now, we've already talked about the diurnal motion. Because of Earth's spin, everything appears to rise from the east and set in the west. And all the stars rise from the east and set in the west. The planets do that pretty much, but they also move relative to the background stars. Planets move with respect to background stars. So the planet, the word planet means wanderer in Latin. Well, we're trying to fit everything that we see in the sky into the notion of a geocentric universe. So we have the Earth at the center of all the motions. And but we see things moving in the sky. We see planets that are moving with respect to stars, and somehow all that has, we want to make all that make sense, but with the Earth at the center, which of course is wrong, right? Because the sun's really at the center of our solar system. But at that time, the name of the game was to make everything into a coherent model that had the Earth at the center. Which is wrong, but they were trying to make that work anyway for sort of philosophical and religious reasons. So what we generally see when we look at the sky and we look at the stars and the planets, if we open our eyes for a minute or so every sidereal day, and we talked about this last time, a sidereal day is 23 hours and 56 minutes of normal solar time, a little shorter than a solar day. So if we lie outside and put our heads pointed north and we open our eyes every 23 hours and 56 minutes of normal time, which is to say every one sidereal day, we would see the stars in exactly the same place, because that's the whole point of a sidereal day. You open your eyes, you see the stars in the same place. Close them again for a full day, open them again, you see the stars in the same place. But if you see things moving along amongst the stars, the wanderers, the planets, and remember our head is pointed north here, we're lying on our back with our head pointed north, and so east would be on our left side, the head pointing north. So what we actually see is the planets moving from right to left, which is eastward. Right? So when we just open our eyes and make this time-lapse film in our minds, we're going to see the planet move to the east. That's just an observational fact. That's just what we're seeing in the sky. But there are exceptions occasionally when a planet would make a funny loop and temporarily move to the west and then pick up the eastward motion. So the eastward motion we call prograde motion, and the westward motion we call retrograde motion. So it's terms. Prograde motion is normal eastward motion. Retrograde is this little western jog that takes from that loop, which is for about a month of actual time, roughly speaking, and then it turns around and starts going in the correct direction again. So it's correct up the eastward direction. Okay, so this is just what was observed, and the goal was to fit all this phenomenon into an Earth-centered solar system model. Oh, is it going to like I have to reprogram it again. So I did this last time. Go to check. Open. Yes. I could program forever. But the next time here, already forgot. Okay, so what we're going to see here is now we again have north up, east is to the left, west is to the right. So we're going to run this. So we're opening our eyes every sidereal day. That's why the stars aren't moving. So we're opening our eyes. This is like every jump here, it's a matter of several days actually. But the stars aren't moving because we're making this movie by opening our shutter every sidereal day. Stars are fixed. But there's Mars. It starts off moving eastward, which is to the left. That's the retrograde loop right there. And then it starts moving eastward again. Okay, so eastward, retrograde, eastward again. And I think these dots are taken at probably about weekly intervals or something like that. So I guess you can sort of tell. It looks like roughly weekly. I can't really quite slow down. I can't read the numbers that much. But anyway, that's what's actually seen in the sky. Now, we know that, just to give you an idea of what's really going on, I don't want to confuse you horribly by kind of explaining this incorrect idea too much without actually referring to what's actually going on. What's actually going on is the sun's at the center of the solar system. Right? What's actually going on in the case of Mars and the Earth is that the Earth is orbiting closer to the sun than Mars is. And it's actually having a smaller orbital period around the sun than Mars is. Mars's year is about 50% longer than our year. Okay? So that means that we lap Mars. We pass Mars by in our orbit. And the actual explanation for the retrograde motion is that when we sight Mars from the Earth, for example, these numbers are sort of monthly intervals roughly. Okay, so we sight Mars from the Earth. We see it back there. So these are the actual orbit. So this upper part is where Mars appears to be against the background star. So it's kind of a two-part diagram. So at point 1, we're seeing Mars over here against these background stars. By the way, east is to the left here, just like before. To the left. So now, at time 2, we take a look at Mars again against the background stars. Oh, it's over against these background stars. That's that marching eastward phenomenon we just saw in the movie, right? So far, it's prograde eastward type motion. Get to point 3, Mars looks like it's over there, still eastward. Point 4 and point 5, still eastward. But when the Earth catches up to Mars and starts to pass it, like a car in the fast lane on the highway, there's a temporary shift in the perspective against the distant background stars. And what we see, going from point 5 to point 6, is an apparent westwards motion of Mars against the background stars. But it's just because of the perspective of us as we pass Mars, right? It's not, physically Mars is still going counterclockwise in its orbit, and we're still going counterclockwise. We're just temporarily doing it as apparently moving westward against the background stars. Strictly a perspective, you could say it's like an optical illusion if you want, that kind of thing. Now, as time goes on and we start getting larger distance from Mars, we start to see the eastward phenomenon of the motion actually take place. Oh. So this is a little animation that just shows what's really going on. This is what we call the Copernican universe, which model which comes after the Earth-centered model that we're starting to talk about just after. But again, this is what's really going on. We have the sun at the center. We have the planets executing these orbits around the sun. And you can actually see that you can see that the orbital shapes are not all perfectly circular. Like Mercury's orbit right here is distinctly elliptical. You can see it's kind of slightly oval-shaped orbit, right? When we look at Venus and Earth, we're actually seeing very nearly perfectly circular orbits. But what's happening during the retrograde part of Mars's motion is when Earth catches up to Mars. That's it. I think it's that one that ends. Right here. Okay. But right at that point, that's when we would see this perspective shift. So what's really happening during retrograde motion is just that Earth is catching up to and passing the planet. That's what's really going on. But the challenge for the ancients was to somehow get this to work in the context of a phony Earth-centered model. So again, this is just a kind of time-lapse photo. There's the ecliptic. The ecliptic is the path of the sun in the sky. You see that the path of Mars in the sky is not right on the ecliptic. So that's kind of an interesting thing. It shows that the solar system is not a perfectly flat pancake with everything in the same plane. Because if the planets were all orbiting the same plane, then Mars would be moving right along the ecliptic like the sun does. And there's a little bit of a departure there. So, the solar system is kind of like a thick pancake, if you will. It's not super thin. It's got some width to it. And here's the eastward motion, westward, and then the